Can anybody hear me? Anybody paying attention? Know that I'm streaming. Okay. Doesn't look like it so far, but I'm going to get a couple more things up here while waiting for people to come in. We're going to do a little talking about Mikey Smith tonight. So anybody who wants to come in, come in. Okay, anybody can hear me? Anybody notice that I'm live? I'll probably talk to myself then. Okay. Anybody here yet? Okay. We talk about Mikey Smith no matter what, so. So, we're going to talk about Mikey Smith. But before we talk about Mikey Smith, okay, nobody can see anything because nothing's up. Okay. Which is good because yeah, I want that window showing. Okay, but not that bit. I know everybody is probably tired of hearing about Mikey, but we're gonna do a little review of how far away Mikey is from me. Here I am in New Brunswick, in this corner here, and it's very close to Maine. Actually, I'm very close to Calais, Maine. It's around here. It's the S is pronounced. And also in New Brunswick, we have Camp Gagetown, which is one of the larger military bases in Canada. And we have Moncton, which is one of the larger growing cities, especially after the pandemic. And then we have around the Ottawa area. Around here is somebody that frequents Unfornicated and a few other sites or channels. And then another one lives out here in Alberta somewhere, I think. But Mikey lives all the way down in this corner of Saskatchewan, right in the middle of the lower part of Saskatchewan. And it's so boy. Took me a second there to get around the S's. But we're famous. We know Mikey for driving up to Saskatoon. Where's Regina? Yeah, this is about 3,000 kilometers away. So I'm not an expert in where the cities are out here. Oh, Saskatoon, found that one. But he's famous for driving to Saskatoon and Regina. And Regina, just now, there it is. It's not actually that far away from Sabonia. And I know I'm pronouncing it wrong. But lately he's been doing chats with Sam, or Flat Earth Reconnaissance. And anybody here yet? No. Okay. And Sam keeps on asking, why did people move to Canada for? One thing was resources. There's a lot of, like my corner of the country was actually settled first, or fairly early. There's forestry. You could see the Bay of Fundy and the Gulf of St. Lawrence and the Atlantic. So a lot of people came to Nova Scotia, Prince Edward Island, New Brunswick for fishing. It's a lot of forestry in the area. Plus, it's during the summer you can pretty much grow anything if you put your mind to it. Okay, just a second here. Get that fact sheet off. There. Probably looks a lot better now. So, I know this is probably one of the world's most boring streams, but okay. Okay. That doesn't prove anything. You grow anything. Just the picture of the barbecue. And my fingers. But you can grow grapes here. Actually, New Brunswick, the Vikings came over here and dubbed like them, at least Newfoundland, Vineland. And you go tulips and all kinds of stuff. You can grow all kinds of stuff here. And the thing is we didn't have a lot of the European rulers fighting over or there was some wars there in the area, but mostly, oops, that got in there by mistake. But you can see it's a very green place during the summer. Some cherry trees. Okay, so that's why people moved here, because there was a lot of resources. You got away from most of the European silliness, and here's the thing. New Brunswick came into being because there was a little spat down here in the 1770s and 1780s. And some people were forced to relocate it. And New Brunswick's population kind of got larger and got separated from Nova Scotia. But we'll start talking about flat earth silliness in a minute here. Just thank you. I can force you guys to listen to anything I want you to. And nobody wants to listen to me anyway, so we'll listen to some of Mikey and Sam stuff.
They're gonna say, oh, SpaghettiOs! Mikey's got some real pictures. What's with the... I've heard Mikey say about cartoons. All these are just computer generated, these things right here.
Oh, this is part of his visit to the Regina Observatory.
I hope we can use the elevator.
Run by Rask.
It's gonna take me forever to get down. I'm okay going up, but not down. So this is the telescope up in this area. You can't see because it's too dark in here, but
As I pointed out before, you use the red light so your eyes can adapt to the darkness. You don't want a really bright light, because if you have a really bright light, your eyes will contract and you have a hard time. The iris in your eyes will contract and you have a hard time seeing things through the telescope. Plus, I almost electrocuted a prof, or one night I was in an observatory and I tried screwing in the light bulb and the light bulb came apart. I told the technician, and I should have left a note too, but I didn't. And the next time somebody used it was for a tour, and it was a professor. And but no, I don't think anything happened. It just oopsie.
Exchange. I'm just gonna push down here for a second. I've got I'm an amateur astronomer myself. Yeah, that's the star Sirius. They're not far. They're not millions of miles away. They're stuck in the firmament, and that is Venus. They're not round planets. And so yeah, I'm here showing people what actual real stars look like. That's the star Sirius 2. I've recorded that through my binoculars.
Oh yeah.
The stars are only about 80 miles away.
I don't know if the stuttering's me or them. But
yeah, these telescopes don't show much. And yeah, it's a lot of cartoons. All these are just computer generated. These things right here.
well, that's the thing about
This
Mikey
is just
is
computer generated. That's not a real picture.
Lindsay. Yeah, thanks for showing up. But yeah, that's the thing is he tells people who have experience or professionals that they don't know what they're up to. So yeah, it's just this is why I nominated him from top left. It's just to me, it's a bit of arrogance that gets me.
Of a planet whatsoever.
Close.
No, it's not even close. I know what they look like. They're just lights in the sky. This, yeah, Neptune is not blue. None of these show up in my. I'm not sure what that's about, but there's. This is kind of interesting. This is a cartoon here too. Oh no, that's a star chart. And when we look at Sky News here, let's look at Sky News, guys.
So we're gonna have to dodge between the feet for a minute or two. Yes, you may certainly.
So here it is here, guys.
It's gonna take a little break.
They got it in the Sky News. That's computer generated there too. Sorry guys, it's really dark in here, but we'll get through these pictures. Oh, this is not good at all. See here, guys? All this garbage here.
So, you were trying
Okay, yeah, I see you guys. Oops.
to take it easy on the stuff.
Oh yeah, no, I didn't realize there was that latch there. Oh yeah. What else, this guy? Can I ask a question about the stars?
Yeah.
Why is there no depth?
Where's no depth?
Yeah, there's no depth to the stars.
I'm not sure what you mean.
They're all stuck in the firmament. I've recorded and documented the firmament on my YouTube channel, and there's no depth to the stars. The stars never move. They're all locked in position.
Well, they do move. They just move really, really slowly.
Yeah, because the firmament's rotating above us.
Well, we're rotating. The Earth's rotating. So
No, we're not moving. We don't feel like we're moving. We're not moving at all.
You don't feel constant speed. You only feel acceleration.
No, so Polaris, the North Star, has never moved ever.
Yes, it has.
No, it hasn't.
Yes, it has.
Yes. Well, everything in space has been moving. But the position, the North Pole was actually once Thubian in the constellation of Draco, the dragon. And it makes everybody who's probably listening to this knows that the Earth makes precesses by a certain amount every year. And over 26,000 years, it makes a complete circle. So it does change. It's just we have such short lifespans that, but it doesn't really matter much in a certain lifespan how much it moves.
No.
Because the ancient Egyptians, 8,000 years ago, built the pyramids facing towards Thuban, which was North Star back then.
How would you prove that? You weren't born 8,000 years ago.
Sir, I think if you don't mind, could you just let the rest of us enjoy the evening?
Yeah, sure, go ahead. But I got some real pictures of stars here.
And they're telling them to leave.
And
I
And Venus.
I think that's
The planets are not balls of gas.
No, and that's totally okay. I think that this takes
Well, it's not okay because you're lying to the public.
conversation for you.
But you're lying to the public.
Oh well, I don't represent anyone, so I this
Here on their own
isn't.
free will.
Yeah, yeah.
Yeah, there's no depth to the stars.
Please, now. You're ruining it for all the rest of us. Leave.
So Saturn.
So sad.
Okay, I'm gonna jump ahead to him and Sam because I think most people have seen that bit.
You're welcome.
Has anybody seen Mikey around for the last week? He's been doing these like weekly things with Sam, which is good for on some levels. But I haven't seen him this weekend, so I don't know if he hasn't got any new pictures because it's been stormy out there. Or if it's been stormy out there around here, it's been snowy. We got one snowstorm the other night, and then Nova Scotia got hit mostly last night. A lot of power out, so I don't know if he's had similar issues or not. Sorry, I need a drink.
And remember, demonstrations always prove or disprove things, not babbling for hours a day, correct, folks?
Oh yeah.
So we're going to demonstrate how the supposed star trails work on your supposed ball theory. Remember, the stars are above all of our heads, and they move in a circle pattern above your heads.
The stars don't move that much each night. It's the Earth moving underneath your feet, and you're attached to the Earth. That makes the patterns and the circles above you, and it depends on where you are on the Earth. What patterns you see?
We got Rossinick. Thank you very much, sir.
Yeah.
So we will do a demonstration here quickly, and then we'll bring Flat Earth Reconnaissance in, and maybe some globies will come in, and we can keep talking about this globe deal here. Let me bring up my screen here a little bigger. So, as you know, you've seen time-lapse videos of the stars. Doing what exactly? Making a circle, correct? That's what they do. They do a circle pattern in the sky, just like this. As if you were going to spin a very large frisbee above your head, right? It's spinning. This is rotating, not spinning. This is rotating. Spinning is a frisbee above your head. Just doing this. That's what the stars are doing, right? Because the sun and the moon go in this direction to the northwest, and they come back from the northeast, just like this, every single day. They are
I all forgot about
above
this bit
your
on this
heads.
video.
Okay, so which head are you going to be? Are you going to be the guy on the equator, or are you going to be the guy in North America, Northern Canada, or are you going to be the guy in Chile? You're going to have to pick one, because all these three dudes are not going to see the stars rotate above their heads like we all do, right? Remember, this is your pathetic model.
Well, the North Star would be over here, so this guy would see it at an angle like over like this. This guy probably the North Star would be near the horizon, and you'd see circles arcing like this, and this guy would see probably complete circles, and this guy down here would see circles going the other way around the other pole. They don't go around each person's head.
Okay. Remember, the Earth tilts, right? I guess so. That's why the sun goes from here to here. What about the moon, morons? How come the moon goes from here to here to here to here twice a month? Twice a month. Ba, 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 ba. Is the Earth doing this twice a month? Going from the southern horizon to the northern horizon, southern horizon.
Okay, let him hold.
We're a big, jolly, happy ball, boop a doop a doo.
Let him show the globe one more time because I want to explain something.
Hold on, I gotta check my messages here. Doing this.
Because what the moon is off an angle about 5 degrees to the equator. The equator is where the sun goes through. So the moon will, one night will be here relative to the Earth, and then the next night it'll be here, and then the next night it'll be here, and the next night it'll be here, next night it'll be here, and next night, and eventually come back around. So that's how the moon goes around the Earth. And also when it's going around, it's also making one rotation every month, so it's tidally locked, so it looks like it's one face is constantly locked towards the face of the Earth.
Through the sky. As you see, here comes Jupiter. Oh, there comes Mars. Oh, here comes Orion's belt. Oh, there comes the Big Dipper. Oh. Remember, the Earth is rotating, right, guys? Okay, now let's move to this guy. How are the stars going to rotate above this guy's head? Like this? Just like this, right? Because it goes in a circle pattern in the night sky.
Hello,
We see
Garden
the
Kitty.
stars doing this every single night. The moon and the sun and all the constellations move like this in the night sky. Correct?
No, it's more off to an angle, not directly over this guy's head.
Or maybe is it the Earth doing this? Is it going like this? Is it wobbling? Does it have a wobbling effect?
It does have a wobble, but it takes 26,000 years for it to wobble. So
Or hold on, maybe it's this guy. We got to put the stars above his head, remember? So maybe it's like this. Maybe the Earth does this. Because remember, it's a circle pattern. Or maybe it's like this. Maybe the Earth wobbles like this. I don't know. Here we are down in Chile. South is not down, by the way, folks. Hello? What about down north? Can you not go down north?
this is more of a language convention than it is a direction. That's all it is. But
What about up south? Okay. Now where are the stars? Are the stars over here now? They're going to rotate above this guy's head, right? Because the Earth is spinning, right? It's spinning, according to them. Like this, correct? The Earth is actually, it's east to west. So it's like this. So I'm not sure how the stars are going to make a circle pattern above any of these guys' heads on this rotating piece of dog manure. Okay? So again, this is your model, Globies. Explain this model to me, please.
we keep trying, and you don't want to understand.
How the stars rotate around this guy's head, and this guy's head, and this guy's head, all in the same direction. Good luck.
Well, in
Moving
the
on.
southern hemisphere, they go the opposite direction.
We will get Sam, Big Bad Sam, to come in the stream. Hopefully, we'll get some globies. They can come and show us their working model, not just jibber jabber and open up their stupid pie holes. But we will get them to come in and they will hold up their globe and show us how their globe works, okay, with the rotating stars above our heads. Remember, the stars are moving, not us. Globies cannot provide any proof of this whatsoever. Zero. Goose egg. Nil. Niet. All right. Pui. A lot of shit going on the go here. So we've got some exciting news. I'm not sure if we're going to talk about it at all, but we will eventually be talking about the fantastic news that other people are doing, along with what Sam's doing. We're waiting for Sam.
Okay,
Doesn't he want to say hello to me?
and this is when Wetcast
Hello.
comes in.
What's happening?
Okay.
What are we talking about? You seem disturbed.
I'm not disturbed. I don't know what you're talking about. I was just live and someone said to me, Mikey Smith's live, go and jump in his live. They've just put a link up, so I thought I would for a laugh.
Oh, we're talking
What's going
about
on?
Star Trails.
Why have you got, like, you've still got the map behind you there?
Yeah.
Do you not believe the final experiment? Is that you still don't believe that?
No, that's garbage.
Why'd you say that though?
Well, Sam can talk about that one. I'll let you go,
Yeah,
Sam.
I've seen Sam. I saw Sam when he was talking to
I don't know why they don't believe in the final. Oh, I know why.
Jaron and
Looking.
Dave McKeegan. So what's the issue? Why don't you believe them?
What did you watch the the meeting?
Yeah.
So, what question do you have?
I wasn't convinced that when you said about the sun and all that going in front of the thing, and they showed you what it actually was, you just sort of laughed and ignored them.
What actually was, well, true version, but what actually was, it was like a fake footage. This is what I see it as, what it was actually. But the thing is that the sun cannot go in between you know, the camera and your face. I don't know. Maybe lately there's new technologies. I don't know that can make that
Yeah, but
happen.
they explained the glare, and they even showed you examples.
Yeah, but the glare can go up to here, not right in front of your face. It cannot just, hide your entire face. You understand? That's not called a glare anymore. It's called a fake footage.
But when they showed you it went actually behind the pole, then it was hidden, and then it wasn't in front of the face anymore.
Well, it was totally hidden. But what video? But the pole of where Maxun was?
When Jaron showed the pole, it showed an example, and when it actually went behind the
Okay.
pole, the glare was there, then it went behind the pole and it completely vanished. And the same thing, Toon's face never blocked the sun, did it?
Yeah, but it never happens in reality. It never happens in real life. People, shooting, the sun, never had that before. Like it's new. Maybe we didn't see nothing.
What do
Well,
you think?
that means-
So what's your theory then? I'm just curious.
I know, yeah, that there's a picture of MC Toon and some glare with the sun behind him or something. I can't remember the picture. I think they got a picture here of Mikey in a similar situation. But no. And here's Mikey's interpretation of Comet Lehman is that this is a hole through the firmament and it's letting light through, and that's the way he sees it.
Gone
Because
already.
you won't let it go. Like, even if you're going to dismiss that's the truth. Even if you're
okay.
going to.
The thing with comets is you have the nucleus, and it does heat up when it gets closer to the sun, and then there's a particle stream from the sun called a solar wind. Tonight there's going to be a big solar storm, large particles in the atmosphere interacting. We call it and then you can see the aurora borealis. Right now it's cloudy because we're the Maritimes, but there's a normal flow of particles that's a lot less, but it pushes the small pieces of dust backwards.
Dismiss the 24-hour sun in Antarctica. Let's just say that was all fake, right? Let's say they faked the whole thing. There's no 24-hour sun in Antarctica. It was all bullshit. If you go anywhere in the south, for the map, any flat map, the sun would have to go the opposite way to the way it actually goes, and everyone can observe that. So what do you say to that?
I don't know what you're talking about. Like from the equator, it goes the different way.
It
That's what
goes
you're
right
talking
to
about?
left. It's supposed to go left
Okay.
to right according to any flat map. If it's just circling Polaris, it would go left to right. It would set left to right, but it goes right to left in the south.
And this is what
Yes.
the stars look like to
Okay.
him.
So what are you
So
saying
what-
that it is a globe because of that?
Yes.
Yeah, but in that case, in that case, you know, everything else has to match that theory of a globe, not just
Yes.
like one thing, you know, because
it
we have
does.
also one thing. There is no curvature. That's okay, 1 to 1, you know, both
There literally
in the
is
middle.
though. Have you never, what do you say like when you see? Do you ever watch Surveyors? Like there's a guy called Baron Rutledge. Are you familiar with him?
Check it out. I'm going to tell you something. You know, the debate of flat Earth, you know, that the Earth is flat or is a globe. You know, we've passed that milestone like long ago already. We know that the Earth is flat. And you know what? What the thing is that
And-
we as, you know, truth seekers, as flat earthers, we don't have anything to prove the way you do. Because we know the Earth is flat. We don't care about convincing you. Anyone
That's
that wants to
ridiculous.
believe...
That's such a cowardly position.
Okay,
We don't
so now
need to prove it.
so now you're starting to curse and starting to insult. Okay, I understand because
I'm not
you
insulting.
cannot
Okay, I'm going to
That's
consider
not-
this.
no,
Sorry,
just-
Whatcast. See
my
what-
tune, even though I don't agree with everything he said. I have no problem. I have no problem.
Hey, Brenda, show me how it works. Come on. What do you want me to do? Does it wobble like this?
Actually, I
But
think
they
we've
don't.
done.
But they don't.
I'm going to go to another Mikey stream. Sorry, Brenda, but I think I've already explained him. Okay.
We won't be pointing my laser at this one. All right, guys, let's see what's happening here. We got a video to review. Hey, where am I here? Goal. Now, what's the question of the day? I have to email myself. Actually, I already did. What am I talking about? We're going to review something later on in the stream. We're doing like a camera test here. We got a camera on sale today, which sounds good to me. Not too bad. Logitech 100 full HD with a microphone, hopefully, I think.
I think this is a web
Yeah,
camera.
built-in microphone, privacy shutter.
Yeah,
and
webcam.
that's the camera that I'm using. So it's it can be worse. So yeah, we will show you the video here. Of course, Mick Looney Tune, when he exited out of the, whatever you want to call it, the shed, the office,
Okay, and this is
the
what.
building,
Actually, this shows the glare that they were talking
the
about
house,
in Antarctica.
the Quonset, whatever you want to call it, when he was supposedly in Antarctica. We will show you. And this is not one of the videos that some of these guys are going to take and say, hey, why is Mike talking about this? He can't prove or disprove this. Why is he doing this? You know, it's not going to be one of these videos where you can say, well, see, Mike took this and he edited this and he did this, and the other person who he got that from, he edited this and put that in there. No. It's not going to be one of those. Because you want to know something? I really hate using other people's videos because I can't confirm any of it. This is why I
Of
produce
course.
my own content. Did you ever think about doing that when you run your own damn channel?
Oh, this is from a year ago.
No, Mike, I never thought about that. I like using other people's content.
The reason why we use other people's content is because we're trying to point out the errors in that person's content. That's the reason why you use other people's content. To point out where they made mistakes. And most of the times, well, yeah, some people do it to be mean. Some people are just doing it just to point out mistakes, and hopefully the people will learn. I'm probably more in the second camp than anything else, but
Makes my life a whole lot easier. Yeah, I know. Because you ain't doing shit about anything. You don't even care that you're getting ass fucked from the government.
yes, Mikey's language needs to be reined in a little bit.
And it seems like I'm the only one who cares. Anyways, flat fry. That is a good one. I like that one. I don't have my pictures.
This must have been just after the final experiment happened.
Experiment? Maybe the first. How is it the final one? You haven't started.
Okay, the language on that was a little iffy, but it was the final experiment as far as Flat Earth, or as far as Will Duffy wanted to do with the Flat Earth, so I was the final experiment. It's actually done quite a bit of damage to their group. Jaren's left, Witset's not doing anything anymore, so, and Lizbeth, one of the Flat Earthers that went there, is not a Flat Earther anymore, so it's done some good, but
Started doing experiments in the first place. How is this the final one? It's the only and final one, is that you should say? I don't know. Anyways, I raced home to record looking for Into Flat Earth for over 10 years now. I know. Thanks a lot, buddy. Yeah. I don't know what you've done, but in relation to looking at my footage, I'm the only one who has recorded a clear star. The only one.
do I have to? I think I have to. People taking pictures of stars all the time. Dee-dee. Yes, we've taken pictures of the stars. We know what they look like. Many, many times. So.
And I'm not joking. I'm not trying to make myself look big or better than anybody else. I am telling you the truth. I am the only one who has figured out that P1000s cannot record the stars through the moisture in the air. And neither can my binoculars. You want to know something?
This is why a lot of telescopes are put on top of mountains or in the desert to get away from moisture. But sometimes you can't help it. You have to have an observatory or observe things near the water.
You can only record the stars when the small dipper is visible. Just because there are no clouds in the sky does not mean you're going to get a clear video or picture of a star. No way.
Okay, if there's enough moisture to obscure the Little Dipper, yeah, that's not a good night to observe, but that doesn't mean it's not clear.
Hey, Jose, brothers. It ain't gonna happen. Mimsy B, what's happening? Hopefully by February, I'm going to sign up at with the group at the art gallery in the big city near here. This is what most of, well, I already know this. This is what all the bigger, brighter stars look like. Capella, Vega, Sirius. What else is up there? Capella, Arcturus, whatever else are bigger up there. I don't know all the names. I don't need to record them all. Hopefully, eventually, I'm the only one who can figure this out. And I'll give you an example how I do it and why. Why it's possibly me. Because you have all the truthers, the flat earthers here in the world. Here they are on this plane level. This is a graph, okay? They are on this graph, this line, this heartbeat that runs from the left to the right to the left. And it's level. And they continue on doing nothing. You see this line? They do nothing. They sit there and watch YouTube videos, debates. They don't tell their family or their friends that the earth is flat. They don't go out in the community holding flat earth signs in front of Walmart. And the line never moves. It's always here. They don't want to grow.
Because if you tell people that you believe the earth is flat, you probably get banished or exiled or whatever you want to call it, but they probably don't want to put up with hearing about it all the time.
In their knowledge.
Plus, again, Saskatchewan is flat, so that may help with the confusion with them.
Or trying to figure shit out for themselves. I do not know why. I don't take... In my life, I said I need to record the Milky Way. And I also need to record those frickin' lights that are moving through the sky at very, very fast speeds. That are not satellites.
So it could be satellites, asteroids, planes. Can't tell without looking at the images.
Someone at my door? No? Okay. So I go from that. Now my brain is just poo-pooed for the rest of the year. Because I'm just like totally focused on getting that done. So I went through doing a lot of thinking, okay? How can I do this? I don't want to use the camera. I cannot use the camera anymore. What are my other alternatives for recording things in the sky? At least that will not make it blurry, that does not have trouble focusing. It needs to be as natural as possible, like the human eye, okay? So I went through getting the testing hunting scopes, the big ones, the ones that you can, not the ones that go on top of guns or on rifles, the scopes, monoscopes, the big scopes that you could set up on a tripod and look far away into the trees. So we tried that. I'm like, no, this isn't working. I tried it. I don't know where I'm looking in reference to what I can only do one thing with a monoscope or a hunting scope. You can only do one thing, and that's cover the one eyepiece and try to figure out where the stars are and where you're going in reference to those stars, because you can't see where you're going.
Okay, I'm going to try something else, but... I'm going to move away from Monkey for a while. Okay. There was something else I wanted to cover. This is another podcast. It calls Demystifying Science. It's hosted by Shiloh over here and Natasha. And this interview, they go talking to a cosmologist, a guy who builds instruments to test the like the Big Bang Theory. So there's a few things in here I wanted to talk about, but
I'm Shiloh.
And this is the place where we search for the theories and ideas that are going to change the world. And today we have a conversation that is one of the most intense and emotional and outrageous conversations that we have ever recorded on this podcast. It seems extraordinary that such a conversation could be recorded on a subject as dry as the cosmic microwave background that is believed to come from the birth of the universe. What we are proposing in this conversation is that the fundamental physical interpretations of the cosmic microwave background signal make it impossible for it to come from the Big Bang. Our guest for the conversation is a world-renowned cosmologist at UCSD, Brian Keating, who invited us very generously to his office, where we sat down and we asked him, if this is how these signals work on Earth, in the laboratory, every single time that we have ever tried to create them, how is it possible that this signal is coming from the Big Bang? And this is where the conversations start to fall apart, because if the cosmic microwave backgrounds...
I've seen this, they fell apart because they don't understand it, or they don't understand what's going on, and they're trying to push their own agenda. But we'll wait to see it.
...signal cannot come from the Big Bang, then cosmology is in a lot of trouble.
Brian probably has a different interpretation of why his reaction is so strong to the ideas that we put down right at the beginning of this conversation. But I want to take a moment to explain why I think that it's such an emotionally charged topic for a cosmologist to engage in. And it comes down, like you said, Nastia, to the particular fingerprint of the light that comes from this microwave background signal. That particular signal is something called a blackbody spectrum, which sounds a little weird and technical, but the reality...
Okay, black bodies can come from hot, dense matter. That's one thing that you're going to have to remember during this.
The reality is that when you heat up a solid or liquid body here on Earth, and you split the light that comes from that glowing substance with a prism, you see a very specific continuous rainbow of color. Now,
okay, there's 3 laws about when you look through things through a prism. They're called Kirchhoff's laws. It's a hot, dense body could produces a continuous spectrum, a low density gas with a hot continuous spectrum behind it will create absorption lines, and a low dense gas will create emission spectrum. So that's from a hot dense body. It doesn't matter if it's a gas or a plasma or a solid or a liquid. As long as it has a certain density, it'll create that continuous spectrum.
the problem with attributing such a rainbow of color like the one in the microwave background to the beginning of the fiery universe is that it's being attributed to a gaseous moment in the universe where the first atoms were just recombining and straining out this light that just happened to be flying around. The problem with that is that whenever we take such gaseous atoms and heat them in laboratories, we don't see a continuous, beautiful rainbow. We see individual lines. Gases produce individual frequencies of light. Sometimes they produce many different frequencies, but they're always discrete spikes in a spectrum.
Because it's not dense enough to create a continuous spectrum.
Now, what gets very bizarre about this is that the idealized form of a heated body is only possible with a very particular body. That particular body is all black. It's a perfect absorber. In other words, it can take all light and turn it into heat, and it can take all heat and turn it into light. And it gives this very particular fingerprint called a blackbody spectrum, which you can check out here. We have no reason to believe, based on any laboratory analysis, that a gaseous plasma, anything other than a heated solid or liquid, can produce such a spectrum. Now, astrophysicists for the last 100 years have acknowledged that this tends to be the case in laboratories. You can't do it. But they always point to the stars as if, well, the stars have this beautiful continuous black body spectrum, or at least something very close to a perfect black body spectrum. It's not quite perfect, but very, very close. If the stars can do it, and the stars are gaseous plasma, well, then why can't the beginning of the universe's gaseous plasma do the same thing? Well, that's where we end the conversation, because there's good reason to believe that the stars aren't a simple ball of gas that we've been taught. That conversation's for another day, and hopefully we'll be having Brian back to discuss that possibility in the future. Whenever Nasi and I are out and about and talking to people about these ideas, one of the first things they always seem to, if not say, they seem to be thinking is, why in the heck am I hearing this from you instead of some Nobel Prize winner? That's a really good question, and there is some precedent for answering that question. One of the central stories of cosmology, if you take an intro astronomy course, an intro astrophysics course, you will almost certainly be confronted with the first cosmological revolution. So for the first couple millennia, most of the first couple millennia, there was a popular cosmology. There were some astronomers who had made incredible star maps. Their conclusion was that all of these bodies, including the planets, moved around the Earth, not around the sun as we understand it today. This is all to say that having an
little nitpick, it's the planets that move around around the sun. It's not really the center of the sun, it's the very center of the solar system, and it's actually located just beneath the surface of the sun. But
ordinary mathematics to back up your cosmology is not sufficient to make it correct. And that's where things start to get very bizarre with the modern paradigm.
I think it's worth realizing, too, how radical of a reimagination Copernicus demanded of every single person on Earth when they went and looked at the cosmos and realized that the way that they thought that they saw the motion of the celestial bodies was not the right vantage point to have. Like, you had to stand at the center of the solar system. You had to stand on the sun in order to be able to see the much simpler, much clearer picture of what was actually happening.
Copernicus came up with the idea. It wasn't until Kepler did the mathematics sometime afterwards that it actually came out. I can't remember let's just look it up. But it was like, because what happened was Kepler came up with the idea, and then Tycho Brahe came up with did the observations out of Denmark, and then Kepler did the mathematics. So Copernicus, he was in the 1500s. I can't remember 1543 when he died. Johannes Kepler was born in 1571, so it probably was closer to 1600 when he came up with his laws. Just the top of my head guess. So it wasn't just Kepler. It wasn't just Copernicus. What Copernicus was hired to do was, the church realized that the date of Easter was drifting farther and farther from the date of spring. It was the first day of spring, so they asked Kepler to redo the calendar. That's why we call it the Gregorian calendar, because it was Pope Gregory was in charge of the church at the time, one of the Gregories, and he had to do the recalculations, and during this he realized that the Earth was going around the sun. Part of the issue was the Earth was going around the sun. That wasn't announced until after his death. But Kepler was the one that did the mathematics, so it was sometime between the two. So it wasn't just Kepler just wasn't Copernicus who changed the world. It was a bunch of them. And then Newton came along with gravity, and Galileo had observations of Jupiter and Venus and a number of other bodies. So, and Flamsteed was actually, I think Flamsteed, there was a British guy, I don't know if it was Flamsteed or not, but he actually observed the moon before Galileo. So it wasn't just one person.
And if we say that the cosmic microwave background has to come from a heated liquid or solid, I don't know how much that changes the story of the Big Bang.
Sorry to change
Something that
space
came
here.
out over the course of our conversation with Brian is that there are so many pieces of evidence that fully integrate into the theory of the Big Bang that it's going to take years, if not decades, if not a century or more, to fully untangle what this means for the story that we tell about the cosmos. But what I do know for certain is that we have to talk about it. There appears to be something very, very strange about the cosmic microwave background, about the kind of signal that it is, about the kind of physical reality that is required to generate it. And if we do not pay attention to that, if we do not think about it, if we do not talk about it, if we do not share our ideas on where that might come from, then we are doing a disservice not just to ourselves, not just to the art and practice of science, but I think to the entire human species.
Okay, I'm going to say something about these two that may come off a little wrong. They come off a little pompous to me.
Because what we do, as humans, ideally, is we search for better stories to tell about how nature works. And the story of the cosmos, the story of the Big Bang, the story of how all of this...
You notice how they're using the word story here? This is kind of like to phrase it like it's a fictional story. It's just a radical royal. It's just a way it's just a way of phrasing it so it comes out looking like it's made up, not based off of reality.
This got here, and the story of what is going to happen to it in the future runs in the background of all of our lives constantly.
And if we're not willing to take a close look at that giant meta story at the heart of science, really, then we are really risking our approach to science in general, which is extremely important because if you look at the way that people interpreted the world prior to science, it was really a kind of anything goes situation. And that's what we're scared of.
And so before we get to the conversation, I just want to express a deep and abiding gratitude to Brian because he did not have to invite us to his office. He did not have to sit with us for this entire conversation. Despite the fact of how difficult it was, he chose to remain and he engaged with us, and I could tell that he wrestled deeply with the ideas, and that is what we need more of. And so I cannot say thank you enough to Dr. Keating for having us, for hosting us, and for letting us have this conversation.
One more thing we need to mention before we get to the conversation is that this podcast is entirely paid for by you guys, the listeners. So we work directly for you. But we just can't do this without your support. And a couple of ways, I suppose, that you can support the project. Firstly, come over to Patreon. See if that is a community that you could contribute to. We get together once a week with our patrons. I love seeing you guys. If you're already a patron, thank you so much for making this happen. Honestly, it's incredible to be supported by such a deep thinking and careful group of minds. It's really incredible. You can also support the podcast by picking up some gear. We design our own gear. We got some different designs down on the YouTube shelf. And we also have some music. We finished our first album, and we've been selling vinyl copies of that record, which you can pick up at a link in the description. All of this goes towards making sure that we can put more and more of our time towards this project.
There's one other last way that you can support us, which is actually brand new. Shiloh and I have almost finished our first book. It is called Paradox Lost: The Material Principles of Natural Philosophy, and it is a breakneck exploration of the history of physics and the future of physics. We asked the question of how it is that physics lost touch with the material mediators probably almost 10 years ago, and this book is the sum total of all of our research into it, and a theory about where science can go next, about how we can take these strange, disembodied forces and fields and actually put a shape to them. And so that's going on pre-sale. It's going to be finished in a few soon. It's going to be finished in a few soon. Shiloh gave me a look to say, be careful what you promise. But if you want to pick up a copy of that, a pre-order, then the link is here And we really hope that you will support us in our quest to finally make sense of the greatest mysteries of physics.
So enjoy the conversation today and check out some of our music as we lead into the conversation. We'll see you next time.
So come out here, put us to the test. There's no prize neath your skies that would see us settling for less. We won't be settling for less.
I think that we should start where we left off last time. So we came 2 years ago and had a relatively abridged conversation that started very broadly. We talked about, what does it mean to quote unquote believe in science? And we ended on this very tantalizing question of, okay, well, we agree that science is not something that depends upon our belief, and we recognize that theories change, and yet everybody seems deeply unsatisfied with all attempts to change the central theory of astrophysics and cosmology, which is the Big Bang. And we've spent the last 2 years really exploring the ideas that are attempting to replace the Big Bang. We had this big conference in Portugal. We invited a bunch of people. It was about the future of cosmology. And over the course of these 2 years, we've come to the realization that there's 3 main pillars that seem to be supporting the Big Bang. And this is elemental abundance in the cosmos. This is the apparent reddening of all light across vast distances. And it is the cosmic microwave background radiation. And given that you have so much experience working with the CMB, this strange, cold signal that comes at us from all corners, I wondered if we couldn't focus the conversation today for the hour and a half, for the hour plus that we have, on the CMB and talk about what would it look like to really dig into it and to ask a very difficult question, which is it possible that it is a signal that is real and measured, but that the story that we're telling about it is not the best story?
See, they're calling it a story and not a theory or a hypothesis. They're calling it a story to kind of demote it.
And to get there, I wonder if you couldn't bring people along for the conversation by starting with a brief explanation or description of what the CMB is and why it's so important for cosmology.
Sure. But first I have to, raise an objection to the fact that my invitation to Portugal must have gotten lost in the mail. In the email. I checked my spam.
Okay, I gotta say something. I've never heard of Brian Keating before, but I'm actually fairly impressed of how he dealt with these guys, but we'll see how that goes.
Folder multiple times. I even run a monthly, office hours with some high-level contributors to my YouTube channel, and one of them was there. He goes by Memes of Destruction. So
Yeah, shout out to Matt.
yeah. So anyway, congratulations on doing
We're
that.
doing another one,
Oh, wow.
and you will absolutely get an
Okay.
invitation, my
This
friend.
time I'll check the spam folder every day. So it's not at all a surprise that the CMB, or cosmic microwave background, is so centrally important, both to the kind of qualitative description of the Big Bang, which I think is a story most people are familiar with, and we can get into more details about it if you like, but I assume from watching and
Okay, I should explain what the cosmic background radiation is. The cosmic background radiation is from basically the beginnings of the universe. It's not the very beginning of the universe. The very beginning of the universe was so hot that they couldn't measure it, but this is like when atoms started to recombine and give off light again. It was originally discovered by a couple of guys, Wilson and Penzance in New Jersey, and they were just trying to set up a radio receiver for Bell, and they found this energy about 3 Kelvin coming from all over the place, and they couldn't figure out where it was. They scrubbed the inside of the horn of the radio telescope, and they did all this stuff, and they still couldn't find where it was coming from, and they eventually figured out it was part of the cosmic background radiation. This is from this image here is from COBE. I don't know if you can see it. The top image here is from COBE, which was a satellite designed to go up and find out more detail. And then they came with the Wilkinson's microwave Explorer and microwave Antares B probe, and it was basically a better detailed. And this is what the universe. This is the heat signature from the early universe, basically. And there's... Why is it taking so long to load? From NASA. You would figure they had fast internet. But that's basically a more detailed version of the heat... Basically the heat map of the leftover radiation from the early universe. So that's what they're talking about.
Being a part of your wonderful show, that a lot of the audience will be familiar with. So I want to go a little bit higher level. So humans by nature are visual creatures. If you look at what's called the motor homunculus, which is a depiction of the weights given to different aspects of the human physiology. So there's a depiction. It's a very strange looking creature. Maybe you can put it in B-roll, but it really shows you what evolution or God or whatever you like has paid attention to. And there's two major attributes of it, and the rest are like almost afterthoughts. Like the pinky toe is really not something we think much about unless you drop something on it, as I often do. There's two things. There's the hands, manipulators of the interactions with the physical world, and there are the eyes. And those are the two most important aspects of the human body that the brain or evolution has really spent a lot of time optimizing for. And so if you take away the mechanical interactions via the hands, which is what I do as an experimental cosmologist, I don't come up with theories. I understand theories very well. I work on aspects of testability and phenomenology associated with it. I don't make new theories, nor is it part of my job description. But I build instruments, and my colleagues and I build instruments, and they're the pinnacle of the construction of this field. There's no experiment that really will top for maybe a long time, maybe ever, the Simons Observatory, which is a project that I co-lead in Chile. So that's dedicated to the optical part, the part that you're trying to glean information about the outside world from its appearance, from the way that it presents itself to you. And as Galileo said, 400 years ago, what a scientist must do the following. He or she must measure what is measurable and make measurable what is not yet so. So he said, he was basically talking about instrument building. You have to construct sensors that translate the paucity of physical signals that we get from the observable universe into something the human mind can then grapple with, iterate on, construct different improvements upon, and so forth. That's what the scientific method is, despite what you were taught in 9th grade biology, right? So from the perspective of the cosmic microwave background, it is the oldest light in the universe. It's not the oldest radiation in the universe. It's the oldest light in the universe. And as such, it has this outsized importance in the uncovering of the physical reality that we are privy to. We can't see things that are unobservable. We can try to make them if they're potentially observable. For example, neutrinos are very long-range carriers of information, cosmological possible information, almost impossible to think about detecting the cosmic neutrino background, other than its interaction with the cosmic microwave background itself. So the CMB...
Why do you say it's the oldest, by the way? Is
the light, the CMB?
Mm-hmm.
So
that apparent, or that's mapped onto the theory that's being made about this, or
so they're just as they're the oldest light in the sense that when you came here maybe a day or two ago, there was a thick cloud layer called the marine layer here in San Diego, which normally comes in May, and we call it May gray, or June, we call it June gloom. And it's a layer of light that represents the last scattering of photons before they reached your eye. Okay, so it's a cloud layer, an overcast layer. You can see everything from here to there, but you can't see anything above it, beyond it, with optical light. You could hear things from beyond it. So there is radiation. Sound waves are a form of radiation. They travel like a plane flying above the overcast. You can hear it, can't see it. The reason you can't see it is because the light is so thoroughly scattered by the water droplets in the cloud layer that's why it appears white. It jumbles up all wavelengths, makes them combine together, and it also prevents. It has a very extreme optical depth. You cannot see through the cloud layer using your eyes. You can see through it with other wavelengths, right? Radio waves go right through it. Microwaves go right through it. So too, the lesson is
They can have a hard time though too.
Yeah, don't they get blocked by the clouds and the water?
Maybe not blocked, but they
Not blocked.
They
So
get us
there's-
in trouble.
Well, so you have to distinguish between what you might consider visibility or blockage, right? So there's wavelengths that are completely obscured by the Earth's atmosphere, but not by clouds. There are wavelengths that are obscured completely by clouds, but not by the atmosphere. And then there are waves that get absorbed by both of them, right? So there's a tremendous amount. For example, ultraviolet light is a very hard time getting through the atmosphere, the ozone layer, right? It also can't get through clouds, so that's sort of an extra impediment.
And we should be considered lucky because that can actually do a lot of damage to your DNA and cause cancer.
But getting back to the CMB.
Dating the light, yeah.
Yeah. So the CMB results from an earlier time in the universe's history when it was hot enough such that there were no molecular or atomic hydrogen atoms. Okay? There was no ability for them to be existing because the universe's temperature was far higher than it is today. So the temperature scales with the redshift, linearly with redshift. And so when the universe underwent an earlier phase, you don't have to posit the Big Bang. You do have to posit the universe was hotter and denser and that there's hydrogen in the universe. But all of these are observable. All of these can be detectable by instrumentations that we build and other teams have built going back to 1965. So we have known about this light, and it was the result of the scattering of light that existed before the CMB was produced. And it existed up until the time the first hydrogen atoms formed. Okay, so behind you is a bottle of water, which used to be ice from the South Pole. See that little Nalgene container there? That was scraped up at the South Pole, and it has melted over the last 20 years since I've collected it. But there it is, right? It's got a lot of hydrogen in it, right? So, but originally it was in the form of snow and ice. You couldn't see through it. But once the hydrogen, once the oxygen, once the water is formed, it becomes transparent. You can see through it. It doesn't trap bubbles. And so it has these properties that we understand extremely well. Hydrogen is the most abundant atom in the entire universe by mass, by number. It's an incredibly important element. We know its properties exquisitely well. We can measure them here. We can measure them in other galaxies. We can measure them on other planets. Their properties don't change. There's no evidence that there's any large-scale changes in the evolution of these atoms or of the properties of the atom or of the speed of light or of the nuclear force, of the weak force. There are no evidence whatsoever that it's changed over billions of years, let alone since the CMB is formed. Right? So once you stipulate that the universe has hydrogen, and the universe was smaller in the past than it is today, that the universe is expanding, and there's infinite amounts of
This is
evidence.
from the redshift data.
Well, there's more than just redshift. I mean, you can measure redshift locally from a variety of different sources. You can measure.
This is more background of what's going on, but it's good to go listen to it anyway. I don't. Hopefully, I don't know what I don't get copyright on YouTube, so.
Intrinsically, what cosmologists do, we would like to measure the distances between different objects. We don't have rulers that stretch billions of light years away, right? So we can't physically measure something, so we make proxies for these measurements in terms of things that we do understand well. And we make what's called a calibration ladder, a rung after rung that takes us from distances on Earth to distances in our solar system, to distances in our galaxy, to distances in the nearest galaxies, to the distances within clusters of galaxies, to superclusters, megaclusters, and then to the farthest distances we can see, which are traced by baryon acoustic oscillations, which we can talk about. There's been a lot of recent discoveries with that recently in the past year or two since we met last, and going back all the way to the CMB. As soon as you go back to the CMB, the universe is too hot to have actual atomic hydrogen. So it has the nucleus of hydrogen, which you just call a proton, or in the case of deuterium, which is also present in that water, which is very crucial, that came from the combination of a proton and a neutron, right? That's what deuterium is. There's a tiny bit of tritium, which is 2 neutrons, 1 proton.
Would it be deuterons at that point if it's a charged version of it, or no?
So deuterons have the same charge as hydrogen, as protons. They're just 1 proton plus 1 neutron. That doesn't change anything, but it's an isotope. So it has slightly different chemical properties, slightly different atomic mass, but it's a minuscule amount because the neutron, it's the effect of the neutron added to the proton doesn't change a lot of the chemistry whatsoever. It changes the density, it changes some other physical attributes of it, but it's not, you can make ice out of it. It's funny, the ice will sink in water, unlike ice cubes of ordinary water, protium water, that will float on water because they're less dense than the water that surrounds them.
But it seems like you're saying that you assume the CMB is an old light source because it maps onto the giant narrative that it is the result of this event that happened deep in the past.
It's not just a narrative. I mean, you can kind of stipulate everything.
Well, evolution's
right?
a narrative. I mean,
yeah, calling it a narrative is slightly, denigrating what it is. Really, it's not like a folktale or a campfire song. I mean, it's the most precisely tested element of physical cosmology.
Absolutely.
That redshift occurs. It's tested in every single cosmological instance.
It's an empirical fact, right? That there is this redshift apparent. It's an empirical fact that the CMB isn't. You can measure it on Earth. You can measure it in satellites above the Earth. You can measure it in weather balloons. These things are all apparent. I didn't mean to denigrate the theory. I'm just saying that we have to stitch a story together as scientists about what this really robust data means at the end of the day.
Sure, but that's an attribute of science, not of cosmology uniquely, right? You have to have some interpretation. When I say F equals ma, is that a narrative?
Yeah.
It's this description of what is apparent. I think that the curve fit for the Hubble relationship is a description of what's apparent, but at least in other sciences, perhaps besides physics, like the theory is the statements of the Big Bang. It would be the story of what causes these curves to look the way that they do. It was pinning this ever-present source or this really robust piece of data to really a story of where it came from in the past. And
I agree 100%, but I would say that F equals ma is also a narrative. It's also a description. It's an empirical observation. It's not provable in the way that the Peano axioms allow you to prove that 1 + 1 = 2, despite your friend Terrence Howard and my friend Terrence Howard objection that one times 1 equals 2.
He did find a breakdown of calculators, which was quite interesting.
He did, yeah. He's a very creative individual. Let me just say that. I have yet to meet him, but let me just say, so in the observational and physical sciences, there's no such thing as proof, right? So and even within the context of mathematics, you could also say the Peano axioms, you could say that Gödel's theorem, those are narratives and stories, but you have to be careful. And there are narratives and there are other narratives, right? We could say the Earth looks flat. That was a narrative that was actually very sustainable. I mean, if you ask 90% of college freshmen on this campus, can you prove the Earth is round? Or is the Earth round? They'll say yes. 100% of them will say yes. And if you ask, well, prove it to me, I would say probably 10% could do that.
Interesting.
And they're, top university in the world. I mean,
it's a very clever little move. That who was the Greek guy? You probably know his name.
It's Aristarchus.
Yeah, I was getting messed up with Aristophanes.
Yes, you're not alone. And then if you want to go really old school, get medieval on them. Literally, you'll say, well, okay, I believe that the sun orbits the Earth. Prove me wrong. I would say 99% of people can't prove that. Even extremely educated people. I like to do
phases of the moon, guys. Or phases of Jupiter's moons.
Well, that doesn't actually prove it. Yeah.
Phases of Venus?
The phases of Venus doesn't prove it either.
Oh, come on.
That could be Venus. So to be devil's advocate, no, the first proof of it was called stellar aberration. So it's the discovery that because of the great distances to stars.
That was much, much later,
It was much later, yeah. So Galileo tried to prove that the Earth, went around the sun by using the Earth's tides as his dominant piece of evidence in the Dialogo, which I turned into an audiobook with Carlo Rovelli and Lucio Piccirillo and other people for the first time ever. We have an audiobook by Galileo.
Audiobook.
But he claimed that was actually in the title of the dialogue. It was, the dialogue in the two chief world systems by virtue of observations of the behavior of ferns, which I don't even know what a fern is, but apparently it's like the inverse of a fjord, and rivers and oceans. Anyway, he claimed that the sloshing motion as the Earth went around of the tides, as the Earth revolved around the sun and rotated on its axis, that's what caused the sloshing, caused the tides. Of course, that has nothing to do with it. The moon causes the Earth's tide. But he was right for the wrong reason. His narrative was correct, but it was completely unsubstantiated by scientific truth.
Okay, so I think that we run the risk of getting a little bit too meta. And the meta conversation.
Can I add one tiny thing I really wanted to add? This is the perfect situation because those guys had an incredibly the Ptolemaic astronomers, who were basically the academics at the time, they had a really powerful model that was super predictive and super accurate, just like you guys do. It was completely badass by all.
And very complicated mathematics, because you had epicycles, and you had sometimes you had epicycles and epicycles, and to me, it just sounds very complicated and messy, because it'd probably be very easy to mess up.
Assessments of the day.
Yeah.
But it turned out to, just need a different perspective a little bit, right?
The crazy thing about the Ptolemaic model is that it is not inaccurate in terms of describing how things look from the vantage point of Earth.
Sure, and so is the flat Earth.
And that's the crazy.
Flat Earth also appears great. I mean, you probably got here not computing spherical trigonometry. You use Google Maps, which is a flat Earth approximation that's local to our tangent point on the Earth's globe surface. So yes, you're right. There are context-dependent things, right? But to get back to the
no, he's not saying the Earth is flat. He's just saying at very local scales, it looks like it's flat. And you can use very local scales. You can use flat approximations.
To the original point, we understand plasma physics exquisitely well. We understand quantum mechanics exquisitely well. And so we know the properties of height. Look at the periodic table over there. We understand all the elements. We understand their binding energies. We understand how they form. Are there things we don't understand about? Of course, there's always going to be things you don't understand. And that's what makes being a real scientist really a lot of fun. However, if you look at the body of evidence, the compounding of evidence that we have, that the CMB results from a denser phase in the universe's history. You don't have to postulate it's a redshift. You don't have to say anything about redshift. You can just say, if the universe was hotter and denser in the past, hydrogen could not be a stable atom. That statement has nothing to do with cosmology. I mean, that doesn't have anything to do with the birth of the universe, right? I mean, what I know you guys are trying to make a very interesting distinction that the Big Bang is a model, and there could be other models, and we can talk about those other models.
I don't think that, no. So we're trying to, the place where we're trying to go is we're trying to say that, look, it seems like there is a really well-characterized body of knowledge about black bodies, about black body radiation, about thermalized radiation. And there appears...
The CMB, we didn't even mention that it is a
Sorry,
black...
I keep switching the camera. I'm used to the fact that when you talk, I switch the camera to you, but I keep... Sorry.
Well, we didn't even mention that the CMB is a black body source.
Yeah.
Sorry.
So it's like the CMB is the universe's best black body signal. And so black bodies are kind of this crazy, unsung hero of physics, because if people in physics know about black bodies and they really care about them, you tell somebody on the street about a black body, and I think that they're going to be like, what? Like, they see the fact that there's Kelvin ratings on their light bulbs, but it doesn't connect to some kind of deeper physical principle. Yeah. And so it's also at the basis of quantum mechanics, so it's this massively important theory.
Well, it's also the link between classical mechanics and quantum mechanics, I would say.
Yes.
It really was a classical discovery that motivated the quantum corrections that Planck made, right?
Exactly.
So you're right. It has this outsized importance, but in cosmology, we observe it as a black body, as you said. It's the most perfect black body we've ever encountered, which means that we can calibrate instruments according to the CMB itself. right? Which means that it doesn't suffer from deviations from there are quantifiable deviations from a perfect blackbody, which have a lot of the Planck formula, or have a lot of the Bose-Einstein properties. So I should take a step back. Blackbody or Planck radiation spectrum is a special case of the Bose-Einstein distribution. So Bose-Einstein describes the properties of bosons at a given temperature in a given what's called a chemical environment, a chemical potential, and interacting with a medium. It has the certain properties that it doesn't have a chemical potential. It's only dependent on one number. One number characterizes every black body that has the same temperature, has exactly the same radiation photon density, and that's the Planck distribution. That's the Planck limit of the Bose-Einstein distribution. So to say that it's a black body kind of undersells it. It's the most perfect black body, meaning it could have 3 different types of deviations: Compton Y, chemical potential, other higher order functions. It could be not appear at all the way it does, but it does. And in fact, we can use it to calibrate all sorts of things, including these lights, right? You trace it to that perfect calibration.
And that's what's crazy.
Yeah.
And that's what's crazy, because on Earth, in terms of the black bodies that we are familiar with and that we use,
Like laboratory ones, eh?
laboratory one, are there other ones?
I mean, yeah, I'm just talking about you said that we... Yeah.
that are in use in the world, because I think that it's not, I don't think it's just laboratories. The incandescent light bulbs also use the same principles.
What?
But the point that I'm trying to make is that there are fundamental physical principles that govern what allows an object to be a black body and to approach perfection, right? So like the main principle of black bodies is that the spectrum of the radiation that they release, it has this particular shape, very abrogated in the high frequencies. It has some peak level of radiation intensity, and then this kind of long tail into the longer wavelengths. That shape, if you take the peak of the distribution, the thing that Planck did is he famously came up with the equation that actually accurately predicted that. There's a physical requirement for objects to appear perfect. And it's
in the laboratory.
In the laboratory. And so that's the piece that we're really trying to understand, because all experimental evidence that we have on Earth suggests that black bodies require specific lattices. Like if you take carbon, a carbon atom placed in a Bunsen burner produces individual line spectra. It can absorb and emit at certain individual wavelengths. Okay, great. You take that carbon and you put it into a diamond lattice, totally see-through to visible light, absorbs really, really well, I think in UV and infrared. Like if you hit it with infrared and UV, it gets really hot. And so it's black to those frequencies. And then if you change the lattice of the diamond to be graphite, as you increase the perfection of the hexagonal lattice of the carbon arrangement, you get closer and closer and closer to something whose radiation profile looks exactly like this predicted perfect Planckian distribution.
And it's a perfect absorber.
And it's a perfect absorber because it can take in those wavelengths. And it's also really crazy because you can't have black bodies that go into the super high frequencies. You can't have gamma rays or even hard X-rays interacting with black bodies. And so it feels like there's something that is deeply material that underpins.
There is, but it's not. It has nothing to do with lattices. I mean, you can have a plasma that makes approximates.
You can't. So the reason that we think that is because we point to the sun.
Not just the sun. I mean, in a tokamak, you can produce a black body.
They don't produce black body.
Okay, I had to look this up afterwards. Tokamaks don't generally produce black bodies. I think it's the cyclotron part of the radiation that produces the black body. But the gas in the tokamak is actually fairly low density compared to the sun, so that's probably why it doesn't create a black body. But I had to look it up, and that's my guess of what's going on.
Body radiation.
It depends on the temperature, the composition of the tokamak. What is the tokamak made of? I mean, what do you think it's made of?
Do you mean the surface of the reactor?
No, not the surface. What is it doing?
What's confining plasma using magnetic field.
Right. So that's one incarnation of it. Sure. Yes. So when you have that, what's in there? What is plasma? What do you think plasma is?
just a super excited form of atomic matter. I mean, it's ionized, I suppose.
It's not atomic. Yeah.
There's no
It's pure
atoms?
electron. No, it's pure electrons.
Wait,
The
so
electrons.
you're telling me
There
there's
are
no-
protons obviously in there too.
Okay.
Right.
Well,
But
yeah,
it's not
that's
lattice.
important.
Yeah.
Well, that's the thing is that okay, so that's really important because we literally have gone down the rabbit hole of this. There is no plasma on Earth that produces a perfect thermalized spectrum. It does not exist.
Like a Planckian
Of course, yeah.
line.
There's
line
nothing that
curve.
even the CMB is not perfect. right? I guess I fail to see what distinction you're making. I mean, first of all, the Planck body, the Planck radiation formula is important because it could only be derived from a thermodynamic standpoint once you accepted the quantization of photonic energy. So that was the key insight. And once you quantize photons, then you have some cavity. That cavity only admits certain wavelengths and then certain approximations. That's why there's a Wien tail, there's the Rayleigh-Jeans region of it. These are all things we observe, not in the CMB itself. We observe these in gas clouds in the Milky Way galaxy. So there's
The
no sense
Rayleigh-Jeans is just one frequency, right? That you're
no,
picking.
it's a huge range of frequencies. Any part,
But you're
basically
picking
long.
one, and you're grabbing the temperature from one frequency, right?
No, but you can get it from, it's a linear approximation to the low frequency slope of the Planck body, black body radiation, which is independent of anything else besides the black body temperature.
But hold on, but the thing that we're trying to get to is we're trying to say that, like, look, there is this piece of this theory that says we have this light, and this light must be from the birth of the universe before there were atoms, because it is.
No, it's not. It's not coming from before there were atoms.
It
It's
wa-
coming from the formation, the transition period between 100% ionized plasma, a pure plasma, and a neutral atomic distribution.
Yeah, I've always
is
understood that it's the
transparent.
leftover.
You were saying like scatter. You're saying it was scattering this early glow.
So a plasma typically has at least two ingredients: ions or electrons and photons. To talk about when you talk about the temperature of a black body, what is it that you're talking about? What temperature are you talking about? The temperature of the photons, the temperature of the ions? What do you think is being
Well, the nice-
characterized, right?
Well, I think
The nice thing about a perfect black body and
Okay, I'm going to explain what these two are trying to say. There's a guy named P.M. Robitaille. He's a condensed matter chemist, or he does experiments with and MRI machines with solids and gases, solids and liquids, and he thinks stars are made out of lattices of carbon, and that's how you get the black body radiation. This is kind of background information. They've had several interviews with this guy, and that's what they're trying to get at, is that you have to have these lattices to have black body radiation. And did I? Yeah, okay, just making sure I unmuted myself. But that's what they're trying to get to, and that's what this entire conversation is going to spiral into. And it'll be there's about another hour left to this interview, so it'll probably be another hour and 20 minutes for whoever is listening.
a laboratory as a cavity is that when whatever is inside of it is at thermal equilibrium with it, it will transform all the radiation from that body into thermal energy. And so its temperature will be accurate and reflect the temperature of the rays.
if you are listening to this conversation and you are enjoying it and you are enjoying yourself and you are
Not gonna make a comment.
Yeah, I don't think we have any problem with the Big Bang or anything like that in this conversation. I think it's more just, is it reasonable to expect such a black body source from anything other than condensed matter with a lattice? Because
So,
we've
again,
never
the
been
lattice-
able to, like, the thing that look, you can't get a Planckian spectrum from a tokamak. You just can't. That's just not true.
You can certainly get an approximate temperature, as you talk about. We have to get to some temperature, right?
Can I just add one tiny little thing?
Mm-hmm.
Like, even with lattice-bound objects like carbonized
When you
substances,
say lattice, hold on a second. You guys keep saying lattice. Do you mean crystals?
just condensed matter.
Okay, so you mean, but you could
So,
have
like-
a fluid that's not a lattice, correct?
You can get black bodies from fluids, but my point is that even when we go into the laboratory and try to create a perfect black cavity, we have variations in emissivity. Like we won't be able to make it perfect, but the way that we get closer is by fine-tuning the lattice. We really change the structure. We don't change the molecules the elements that go into it.
That's a lack of our ability as experimentalists to construct something that's a perfect emitter and absorber. By definition,
but the way that we get
exist.
closer is by tuning the lattice. Isn't that interesting?
But when again, you keep saying tuning the lattice.
We
we only
change the
have
crystal structure of the substance.
But again, you just admitted it's not crystal only, right? It could be a liquid, which is not a crystal.
The emissivity is how much light is re-emitted from the particle. So if you have something that absorbs 100% and gives off 99%, you have a 99% emissivity. And yes, I can't pronounce words. But that's basically what they're talking about here, is that you can't get 100%. Something can absorb 100% and emit 100%.
Liquids have structure inside of them, and so basically, like, the thing is that even
liquid's definition is that it doesn't have structure. That it assumes the shape of the container. There are gases and so forth.
Like people study water, it has a transient lattice structure. That's actually what I do my PhD in, was in the transient lattice structure of water. So it's like
you can certainly form it into a crystal. Yeah, that's true. But
no. Like liquid water has lattices that are transient in the liquid matrix. This
like
is
the water molecules will swap out, but the structure still remains. It's quite perplexing. It's a really beautiful phenomenon.
Yeah, that sounds interesting. It doesn't sound necessarily relevant to what we're talking about, but
no, what's really cool is that to get really so look, the CMB is the most perfect black body we've ever measured, no doubt. To get even close to starting to get something that looks even sort of like that in the laboratory, we can't just use a black substance. We can't even just use carbonated substances. We have to get this really beautiful layering of this hexagonal planar structure of the lattice, and that's how we get close to making a perfect black body.
No idea what we're talking about, guys. I'm sorry.
Okay.
There's no such thing as we can make an oven out of iron, and then we'll have, when you guys say we can't measure it, we can approximate, what are you talking about? I mean, we can measure it
to get the emissivity as close to 1 as possible.
How do you measure the emissivity?
Emissivity is a really complex measure. It literally has to do with lack of reflection, from what I understand, the way that there's like this NIST database where they test these things out.
Yeah, and what are those predicated on? The atomic structure, the different structure, but it has nothing to do with
structure. It's not the atomic structure.
But you just mentioned like hexagonal. I mean, that's relevant for carbon or something. Iron doesn't have
they use these soot-covered boxes to get the highest.
Yeah,
possible.
we do use that. I should say because we have to have very low reflectivity, high absorption, baffling in our telescope. So we actually have mimicked the interstellar dust clouds that are actually even better than anything we can do on Earth. That have gas clouds. They are not lattices. They are
dust
gas
is
clouds.
Interesting, yeah.
Yeah. So we mimic them. We measure their properties. We found that we have to make the substance. One of my friends invented. It's called Bach Black. It has carbon. It has glass spheres embedded in it. It has silicate in it. It has a whole bunch of amalgamated stuff. We use it in an epoxy matrix. We suspend that inside of our telescopes to absorb stray reflections, because just like with cameras, you see the reflection in the camera. That's from ghosting. We don't want these photons that have been traveling for 13.8 billion years to be reflected and scattered back to the sky. That doesn't help us at all.
Absolutely.
Right? So we want to absorb them on our detectors. So we're very good at optimizing for these things. So we know how to do these detections. We know how to measure things. Our job is not to measure emissivity. But again, this is like, do you guys want to talk about material science, or do you guys want to talk about the properties of cosmology that render a physical observable into something that we can then use to measure the scale of the cosmos, the age of the cosmos, the composition of the cosmos? Because it really doesn't depend on if carbon. If we didn't use carbon and we use silicon.
Sorry for not talking much, but there's not much to say.
It doesn't
right
have
here.
the exact lattice structure.
And it's not as big of a black body.
Okay, but so what? I mean, how do you know?
Okay, so the so what is here. The so what is here. So the question that we started with is it possible that there's this piece of evidence that has been measured extraordinarily well? Nobody's arguing about the quality of the measurements of the CMB. The thing that we're asking about is look, there is I know you don't like story. There is an interpretation of that data that is said to be evidence of the Big Bang. Like, the CMB is said to be evidence of the Big Bang because of a series of frames of the movie that all sum together to lead us back to the beginning of the universe.
The chain of epistemological
Absolutely.
evidence, yeah.
Okay. So what we're saying is we're like, hey, Brian, there's a crazy thing that we've come across. We've read Planck. We have been studying black body radiation. We have been thinking about it tremendously. Shiloh and I literally, at 3 a.m., we will wake up and I'll be like, yo, dude, are you awake? And he'll groan and I'll be like, okay, so I've been thinking about lattices. And then we talk for, an hour until finally we can fall asleep. Like, this is something that we spend all of our time thinking about. And we're like, Brian, I think that there's something about material science in the laboratory that is relevant to cosmology that needs to be addressed.
Okay, let me just maybe fast forward to some possibly more interesting things than this. I mean, for me, this is not very interesting, but I will address
But why?
it.
It's the centerpiece of the theory. Like, if
The deviations from perfect emissivity for 100% absorption and emission, the deviations of, say, the what we consider the CMB frame to be about, compared to any other model that purports to explain the CMB's existence, there's 1,000 sigma difference between the postulate that it's dust, that it's caused by starlight scattering or iron filings. Those are completely ruled out, excluded at literally thousands of sigma because of the precision of things like Planck and other things. And let's say I stipulate that the emission, the CMB it has a 10% emissivity versus what you might expect it to have. Let's say it should be a perfect absorber and a perfect emitter at all frequencies. Let's say it's 10% off. I think it's the actual number, the Compton Y parameter, is 10 to the minus 6. So we can't say it's 0, right? You'll never be able to say with our instruments that it's 0. It's perfect
really
black
good.
body. Right. It's
Yeah.
extremely good, right?
It's really
So
good.
let's say I multiply that by, I give you guys 1,000 times more. That doesn't change anything about, say, the Hubble constant, the age of the universe, the composition, when the
is true.
CMB formed, what the composition was in the CMB. By the way, we don't just get this from like hydrogen alone and the proper. We get it from every single one of the elements that was present then in the early universe. We get it from everything that's interacted with the CMB. There are galaxies between us and the CMB that are at a high redshift. And so they will absorb different wavelengths of light. They have different compounds within them that will cause absorption. And it exactly matches the fact that the CMB at redshift of 1,000 had a temperature of roughly 3,100 Kelvin. And today we measure it to have 2.7 Kelvin, so we get a redshift of 1,100 from that calculation. And if this galaxy is at redshift 1, it will show this exact same scaling by the expansion factor, and the chemicals in that galaxy will exactly absorb as they would at our galaxy at redshift 0.
But that doesn't preclude, like.
But I'm saying if I change the emissivity, if I say that we got the emissivity, we made it boo, the emissivity is 100 times bigger.
No,
or 1,000 times bigger.
we're not
Right.
saying that. That's not what we're saying. We're literally saying, Brian, what if the source of the CMB is not the story? We're not telling the correct.
You cannot change that. You cannot change the story by that much.
Why?
Using emissivity alone.
Well, no.
Or using any property of the black body.
Hold on. We're using a theoretical principle here. Like, we're arguing from. I sound like a dweeb. We're arguing from first principles. We're saying, look, there appears to be a principle of fundamental physics. There's a principle at the heart of physics about black body radiation. It is a very well-studied phenomenon on Earth. And on Earth, the lattice structure, the hexagonal planar lattice, is the only structure that is capable of giving a black body.
And this is more robotized stuff. So they're basically trying to state that there's some kind of hexagonal structure in the CMB, but carbon didn't exist back then.
I know.
It was just hydrogen helium.
That is, if you look up,
It is true,
it
though.
is true.
So you guys say hexagonal lattice structure.
Yes. So like.
So what is a lattice? I mean, you guys are so flexible with what you're calling a lattice.
No,
I can't believe that we're talking
all
about the
of
same
these things are made out of lattice, like everything in this room that is condensed matter.
When you say a hexagonal lattice, first of all, there's at least 3 different types of crystal structures, lattice structures that can be present that don't have hexagonal close packing. Is that what you're talking about?
I
Hexagonal
think
close
graphene's
packing?
probably the closest that you're going to get.
Right, so
Like
that's a true hexagonal two-dimensional planar lattice,
That's right. That's right.
But
it's a
if I
really
make a
good
black
absorber.
okay, so if I make a black bot, if I make an oven with a pinhole a classic black body cavity, and I make it out of iron, completely out of not carbon. There's no carbon in there. Purified it. It's 99.9, 17 nines purity. You're saying that will be so deviant from what we call a black body that would have some material effect, and it would cause some misestimate
It'll give you the wrong
of
temperature
macroscopic.
for sure.
Yeah. It will. That's the crazy thing, Brian.
Yeah.
That's the crazy thing.
I said perfect. It's a
It
perfect
won't
iron lattice.
thermalize. It won't thermalize the radiation, so it'll give you the rays will be the wrong color. It's like MRI machines would cook people's heads if all cavities gave the same radiation temperature, right? Like
We're talking about like 80
they're
different things here,
reflective.
guys.
They're
This is-
reflectors, right?
This
So-
is kind of frustrating because this is nothing to do with cosmology. You guys are talking about black body. So let's say you guys want to talk about black
bodies are at the
bodies.
center of cosmology.
They're
There's
absolutely
Brian, there's a
important to the
cosmological
CMB,
Brian,
right?
there's a
How do you explain the fact that the temperature predicted that's required for the formation of deuterium, the first non-trivial nucleus, that is predicted to occur at a temperature, which you must know what that temperature is, right? What is the temperature that deuterium fuses at?
I don't know. And
Okay, so you guys don't know that, but you know everything about hexagonal lattices that supposedly have such a big bearing that you get how much you get the temperature.
That's what I did in my PhD work. That's what I published on.
I mean, a lot of people do PhDs, but I don't.
I published on
but you're
this
not you're not studying radiation physics, right? Let me just ask you, how big a difference? Let's say I heat up an oven, whatever that means. I guess you guys we can't talk about temperature. Like if I heat it up if I heat up something to 1,000 degrees Kelvin, and it's an iron, it's made of pure iron. There's nothing else in it. There's no carbon. There's no nanotubes or nothing going on with it, right? I heat it up to 1,000 Kelvin, and then I have a spectrometer. And then I say from the spectroscopic data, what is the temperature that cavity is heated to? It will be off by how much, according to you guys?
It depends
Parts
on
per billion or factors of 10.
Is it in a cavity or is it able to?
You have a pin. I just described it. It's a classic black body is a cavity that has a tiny little hole, so that do you know what the cavity hole size has to do with it?
It has to not allow reflections from the room in, basically.
No, it has to ensure that you have incredible numbers of scattering before the light emerges. So it has time to do what? To thermalize, right? That's what a black body cavity is. That's what Planck constructed this thought experiment. Obviously, you can't build it perfectly because no photons would get out, and the wavelength of the aperture of the black body constrains what modes of light can get out. But you're saying, how much would that change the temperature of the black body? As some radiometrist, not a cosmologist, not a lattice expert, not a nobody. What would they measure the temperature to be? I say it's 1,000 Kelvin. What do they say it is?
It will scale by the emissivity. So whatever percentage of one that it is, it will scale. It will be called a gray body as long as it has a Planckian distribution.
Sure, technically it would be a gray body, but how much will you get to misestimate the temperature of it?
It depends on the lattice. It depends on the organization.
So for iron, you should know what the emissivity of iron is.
How pure is the iron?
I just told you it's 17 nines pure.
I like.
It should be some fraction of one.
Yeah.
Of course, it's a fraction of one, but that fraction is very important. Is it a part per trillion or is it a factor of 2?
Well, it depends. Like, look, let's take a step back from this because you're asking a question that you can look up in a table. Like, we can go and look this up, and there's a database that tells you exactly the emissivity of this stuff.
Emissivity is sure.
Okay.
And I agree. Emissivity is never going to be perfectly equal to 1. But that is what matters for cosmology is what temperature do you measure the spectrum to be for these imperfect black bodies, right? That's what you're saying. You're saying all cosmology is predicated on...
That's not what I'm saying. What I'm saying is that perfect thermal spectra are produced by a certain kind of substance.
Specific arrangements of atoms in condensed matter.
So basically, if you don't have this certain arrangement in condensed matter, you can't have a black body, and you can't tell what temperature everything is, and therefore you can't tell how old the universe is. I'm going to skip ahead a bit.
Things I still, if you agree that we can measure the temperature at which hydrogen forms at in any laboratory on Earth, then you can also stipulate that if you can measure at some different temperature, you could say whether hydrogen formed at that time or not, right? So you could say if the temperature of the universe is above a certain value, it cannot form because it's simply going to be ionized, correct?
I guess I'm not sure that you've measured the temperature of the universe yet, that's all.
Okay, so to say that you don't believe in the state that the observations are credible?
No, they're great observations. The instruments are fantastic.
I'm going to skip ahead.
I want to stipulate let's say I'm totally wrong. Big cosmology. Eric Lerner's right. Convince me. I'm totally. I'm not. Just let me finish.
We're definitely not flying that flag.
Let me. Well, you mentioned alternatives. You mentioned like all these things hinge on this one thing.
The world of people that are saying that there are different ways of looking at this is so big you cannot imagine it.
They think it's big. It's probably in the hundreds of people compared to thousands or millions of people. Well, there's probably not many cosmologists in the world. Obviously, yeah. I think when I was in university, there was probably 10,000 professional astronomers. It's probably grown a bit since then. But I don't know if cosmologists fit in there, but you got to figure that there's all kinds of different subdivisions in there. So there's not many cosmologists in the world, but there are a few different subgroups of alternate cosmology, such as the electric universe and Robitaille and a whole lot of other people. Most of them they don't like relativity. So
imagine it. I also imagine the world of credible people.
They are credible and they are reputable. And
give me some names though of people that don't believe that the CMB is representative of a black body state originating from an early hot dense state.
I don't know.
Name some people that.
I don't know, but I don't want to make
PhDs.
this about belief, though, right? That's
no, but you just said there's a world of people that's so big I can't believe it. I can't believe you're right. So tell me some names of people that are credible, published, scientifically vetted.
I think he's starting to lose. He's politely losing his temper here.
Have laboratories, have done experiments, have attempted to make these measurements, or is it people speculating because they have tokamak reactors, they have their own things they want to do in Pennsylvania or wherever? Tell me the names of these people, these credible people that you guys are mentioning. That's this world of people, Anastasia. You should be able to tell.
Well, I don't necessarily think this is about appealing to anybody's particular authority. It's really about trying to understand something.
I'm just mentioning. She mentioned.
Yeah, I know, but I don't think that's what you wanted to get into.
No, I think that I don't think that the point is to name names. I think that there is a really serious tendency to denigrate anybody who comes around to say, "Hey."
No, you're wrong. Scientists are the most denigrating it. They're the ones that will denigrate their opponents, scientifically speaking, not just based on their personality. I'm not making ad hominem attacks. I am asking, do these people have credibility? I get 100 emails a day from people that have solved these problems and the theory of everything has been unified. Quantum gravity exists. Right? So you get all these emails, right? There has to be some gatekeeping, right? I'm sorry. If you say that there's gatekeeping is bad, I fundamentally, thoroughly disagree with that. Just as I have a gate around my pool at my house, we have a gate around our country. We have gates that serve certain purposes. We have gates on this campus to keep certain people in, certain people out, right? So
who are we keeping in on campus?
Who are we keeping in? Hopefully the professors. No, hopefully the professors do actually doing some work. But philosophically, you guys will not tell me the degree to which this matters. I will stipulate the CMB is not perfect. I will stipulate that Diamond is not a perfect black body.
It's actually really
not a black body.
Okay, fine. And I'll stipulate whatever.
Gray.
So you'll find these different things. You can measure their spectrum. You still haven't told me to the degree that we assume in our model, which you call story, whatever, in our model of hydrogen, the simplest element of the periodic table, the most well understood atom that exists, the foundation of all of modern physics and thermodynamics and all sorts of other things, astrophysics. You still haven't told me how big of a difference are we talking about here? Because let's say we had the universe was made of carbon, so it was a perfect black body, or it had the potential to be a perfect black body. Again, I don't agree with that, but let's just say it was made of carbon. How much of a difference would we underestimate or overestimate the age of the universe, the big pillar, or the fact that the universe is expanding? Would we say the universe is contracting? Would we say the universe is 1 trillion years versus 13.8 billion years? Tell me, give me the brass tacks here. Tell me exactly what are we getting wrong and by how much? Tell me the quantity.
Can I take this one maybe? I mean, I can see the confusion. So we're not saying that the CMB is an imperfect black body. We're actually suspicious of how perfect it is. We think, wow, that's a really interesting phenomenon that you measure something that should come from condensed matter here on Earth. And what's really interesting is that the CMB was first discovered on Earth, then it was really tightened up in terms of error bars by these weather balloons, and then it was measured by.
It wasn't first discovered. Again, you guys are these are simple things. It was discovered in cyanogen molecules in 1947 in our galaxy.
Well, there was a guy who proposed that the cyanogen temperature was perhaps a option, like a source of the universe's temperature that was
No, it's not a
related
source
to
of no, no,
the
no,
Big
no, no.
Bang.
He measured it as a detector. He used cyanogen.
Okay, I don't really know much about the cyanogen measurement. Maybe I should have looked that up, but somebody found out before Wilson and Penzance, but.
In the Milky Way galaxy and its absorption features, which, as I mentioned before, was been used in other galaxies, not even just in the Milky Way. And so when you say something's measured on Earth,
Hold on,
again,
but he wasn't like when he published the cyanogen measurements, nobody accepted them as being evidence of the Big Bang. The provenance
Thing with the science is you can't take one piece of evidence or one theory. You have to find multiple streams of evidence. A lot of people go with general relativity, how Einstein predicted that light would distort a star's image by so many degrees if you're looking at during a solar eclipse, because you're looking really close to the surface of the sun, and that's where gravity is the most. The other one was the precession of the orbit of Mercury. Mercury's orbit changes very little over a century, is like less than a second, but people measured it over time and found that Mercury's perihelion changed over time, and general relativity predicted it, and it was one of the ones. So there's you look for multiple sources of evidence. You don't just take one source of evidence. So the guy in 47 could have found the cyanogen molecule, and then Wilson and Penzance found more evidence, and then more evidence came in over time, and that's how the cosmic background radiation was nailed down after so much time.
of the CMB
data.
as being what's that?
It was in the data. I mean, who
Hold on,
cares
it
what
wasn't a black body either.
They
It
didn't
was
have
just
a
a Rayleigh
concept.
Jeans approximation at best. Like they're just.
It's a molecular absorption feature that
Everybody
occurs in
was predicting temperatures. You know, people were making all of these crazy
the dominant
predictions.
paradigm was the universe had no temperature, or it was a concept from starlight. That was its dominant temperature.
The steady state people were arguing that, yeah, at first for sure. But my point is that so they measure this incredible thing right here
But
on
they didn't
Earth.
do it on.
Well, they
Again,
do.
you're
They
saying
measure.
There's an alternate view of the universe called the steady state. It has generally been proven wrong. Is that there was no Big Bang. It's just that material kind of forms to look like the universe is expanding, and it came from one point, and there wasn't a central point. But there hasn't been much evidence for a steady state universe. So.
In the black body.
What do you
here
mean
on
on
Earth?
Earth? What do you mean the black body on Earth?
Well, there was a horn antenna that Penzias and Wilson used in Holmdel, New Jersey, to
Yes,
get a
very familiar.
signal that was measured first terrestrially.
Like
Oh, gotta forget another thing Robitaille thinks is that since this radio antenna was near water and the WMAP and Kobe were around Earth's orbit, he thinks it's water causing the signal from the cosmic background, causing what we detect as the cosmic background.
got several frequencies. At first, it was
But what does
also
it matter?
Rayleigh Jeans.
What if he built it on the moon? What does it matter that he made it on Earth? Or
Well,
that
that's
Penzias
what's
and Wilson
interesting.
built it on Earth. And
Well,
by the way, I
because
knew
we have a lot
both
of
them.
condensed matter here on Earth, right? So, like, they go up, right? They go in these weather balloons. They're still getting it. It's a perfect black body. They go up to.
It's not perfect.
They do the
Nobody
Kobe
ever
satellite,
said
right?
it perfect. Nobody's ever said it.
We agreed at the beginning of this conversation. It was
No.
very near
I
perfect.
said it.
It's the near.
But there's a huge difference. There's an infinite difference between nearly
Fine.
perfect and perfect. If I say the Earth is a sphere,
Yeah.
am I saying it's a perfect
It's really
sphere?
good.
It's not
I'll
a perfect sphere.
I'll go with really good. It's really, really nice.
It's the best one that we know
They
of.
measured at Kobe. It's really, really nice.
Until that was in the year 1992,
Yeah.
right? Yeah.
But that's where all of the direct measurements of the CMB come from.
That's outer space, right? But you said
I
it was
mean,
on
it's
Earth.
very low Earth orbit,
No,
right?
it's not in low Earth orbit.
Kobe, absolutely.
Kobe was in Earth orbit, but it's not on the Earth. There's no
it's-
atmosphere. The atmosphere.
It's very near a bunch of condensed matter is what's interesting.
So the condensed matter of the Earth affects what properties of the radiometer that FIRAS used, the Far Infrared
Well,
Absolute
it's the
Spectrometer.
closest source of anything that approximates what would give a black body Planckian spectrum in a laboratory is the Earth.
What is the Earth?
The
Earth itself is I thought carbon's a black body. Nothing else.
The Earth, here's the thing. You can have a black body, a Planckian spectrum that gives you the wrong temperature. Then we call it a gray body, right?
Yeah, you would impute
because
the
it's
wrong
got
temperature, right.
imperfect emissivity. Perhaps the Earth is a gray body in some sense. I mean,
It almost
the Earth
certainly
is
but
like
what?
70% water, the surface of
Wouldn't
it.
that
anyways.
then decrease the validity of your argument because you're contaminating
would
a
give
black
the-
body with a gray body?
It would give
and
the
I-
wrong temperature.
So, but we don't see any evidence of the CMB being afflicted by gray body attributes. So, how do you reconcile that? If the Earth is this big contamination source,
Gray bodies have a shape that looks just like black
by the way, the
bodies,
amount of-
but they give you the wrong temperature.
the amount of do you know what the atmospheric density is at the height of Kobe's orbit at 250 nautical miles in the polar orbit above the Earth? Do you know what the
Probably not much.
It's effectively zero within our measurement. So it's not an atmospheric effect.
No.
It was shielded by over 100 decibels. This is something
No,
that
it would
I
need a
worked on.
lattice. Yeah, it would need a lattice.
So
If
where
we're
would there be
looking for
some
something-
lattice floating around?
Yeah, so I mean, like this kind of goes, you know, I don't. I'm not saying I know the source of it. One possible reasonable
but if you're
candidate, if you're
questioning
looking for
it,
a
it's like-
if you're
it
looking
sounds
for a
like I'm talking- yeah.
If you're looking for a hexagonal lattice, there's an enormous set of hexagonal lattices in the surface of the of 70%.
So wait, so
of it.
other atoms, any atom that if I made iron into a hexagonal lattice, whatever that means. By the way, hexagonal planar versus
Yeah.
hex cubic close packing. I don't know what the difference is.
We have reason to believe, like this is perhaps where my own research is relevant, that water does form hexagonal planar lattices, actually, especially under pressure in bodies.
I'm sure it could.
At surfaces.
I don't dispute
right.
that.
So that's kind of interesting that there is a
How does that affect the
substance-
age of the universe? Or the
Well,
Hubble
the
constant?
question is whether or not what you're claiming is a cosmic source is in fact cosmic. Because if it's actually coming from the Earth, then it's no longer...
But you just said the effect of the gray bodiness caused by I could put a whole spacecraft made of carbon nanotubes or whatever Anastasia was mentioning before. I put those right in low Earth orbit or whatever, measure things from the Planck satellite, which also measures this, and the inverse Compton scattering.
Is the Planck the one at L2?
Yeah, Planck
Yeah,
and
so they
WMAP,
never-
both WMAP and Planck.
They
are
didn't
at L2.
measure the monopole at L2 or the dipole. They just had used calibrations from Kobe Fear. So they didn't measure the CMB there.
They measured
like
the
a
annual
differential rate.
modulation of it. Yeah, they measured the modulation of the dipole.
They didn't actually record the CMB.
But they were measuring something that wasn't the CMB.
They were
were they
assuming the temperature of the CMB and measuring a differential radiometer that looked in two sides of the sky and compared.
Yeah, but as you must certainly know, you get when you expand the multipole expansion of the CMB, you get a term that depends on the absolute temperature.
That's just an expansion, though. They didn't directly measure the
They
monopole
measured
the
measured-
dipole. They calibrated off
But
the
all
dipole.
those are connected to the. No, they can't.
Okay. The dipole and the CMB. You can see there's these two lobes. One's red and one's blue. And okay, the blue one is when the probe was headed towards the CMB, and the red was when it was coming away, because it's an orbit around the sun. And that's how you get this dipole effect. And it's one of the things they measured.
Actually calibrated from the different. Again, you guys are making very simple mistakes.
No,
here.
it's not
They
a
don't
mistake.
calibrate from the monopole. They don't calibrate at all.
No, they
from the
calibrate
monopole.
from the dipole and
They
Kobe.
calibrate from not only the dipole. There's multiple dipoles, right? What is a dipole caused by?
The proper motion of the Earth with respect.
No, not the Earth. The spacecraft is what is measured.
Well,
right?
it's
So the
rolling
spacecraft.
around with the space. With
No, the
Earth.
spacecraft has
It's
multiple.
attached,
No, it
yeah.
also is attached to the galaxy, Sheila. So there's many different dipoles that they can measure. This gives you multiple avenues of attack, just like looking at the paleontological record.
Okay, this actually crosses over to flat Earth, because they say you can't measure the motion around the galaxy or around the orbit. These dipoles actually are measuring the movement around the sun and around the galaxy, so it has been measured.
gives you information looking at the geological record. They give you multiple things that all point in the same direction.
Isn't that crazy? They didn't directly measure the CMP at L2. Like, why not? That would have been so
Do you know
easy
how
to
hard
do.
it is to measure this?
No, they could have used the same kind of horn that Furious was using.
Absolutely. So you guys, again, this is
That'd be a
now
cool
slightly. So the deviation from the black body that they measured in terms of Compton Y, gray body, emissivity, and the deviations that will also be present in the Sunyaev-Zeldovich effect and the inverse Compton scattering that occurs, which I'm assuming you guys know, but I'm not 100% sure because you're not experts in the CMB. But those effects, they all come out with the same exact temperature, and the deviations are at the part in 1 million from Compton Y. So now you're going to tell me that effect, whatever that is, and no scientist is saying it's a perfect black body. They'll say it has this chemical potential limit and it has this Compton Y distortion. There's another type of distortion you can get in very strange cases where there's energy injection that occurs later. We've limited all those are parts per million. That has no bearing on the age of the universe or any other statement of the fact that the universe was smaller in the past. Then I add, hold on, let me finish. Then you add on to the fact that we measured cyanogen in our own galaxy, you measure other galaxies have cyanogen, you measure other molecules and the spectral and vibrational characteristics of a book that's right there that has, by Charlie Tennant, that has the rotational and vibrational spectrum of literally 1,000 molecules in the microwave spectrum. They all come out with the same value for the temperature. How is that? How is that orchestrated? By what mechanism did a galaxy at a distance, let's call it a distance, not even call it a redshift, some distance of a million light years away, or even more, because that's close. How do they all have the same temperature?
Okay, so can I take this one? Like, if there is a background temperature of the universe, is not the question. The question is the background temperature of the universe coming from a gaseous substance 13.8 billion years ago prior to the existence of atoms? Or is it some kind of signal being produced by the thermal equilibrium of objects with lattices spread through the universe today?
That didn't exist. Where did carbon
What do
come
you mean
from?
it doesn't exist?
Carbon
No,
didn't exist.
today. Like, that's the whole point of the argument, Brian. I'm literally saying, if you cannot have black body light come from something that does not have a lattice,
Nobody has ever published, as far as I know, in the cosmological
Brian, I hope
context.
that you do not think that the quality of an idea is dependent upon it being published in a scientific
come on,
journal.
this is a ridiculous argument. If I say to you, I've studied the Kennedy assassination last night, but I don't have a PhD in chemistry. I don't have a PhD in ballistics. I don't have a PhD in meteorology in Dallas in 1963. Is that all the same thing?
Brian,
do you take all people's credit? Like, anybody has an idea, we're supposed to weight those equally in some
Brian,
easy
I'm
formula?
literally sitting in front of you, and I'm like, look, the fundamental theory that is at the basis of black body radiation
Well, technically, you're supposed to accept it all equally if they have evidence to prove their point. But if they don't have any evidence to prove their point, or their evidence is weak, then you shouldn't really take them seriously. A PhD just proves that you've done the work, that you've gained a lot of expertise in that field. But if somebody comes up with an idea and there's evidence that it's true, then you should take some credence to it. But a lot of the stuff doesn't have the evidence to back it up. It's just, I'm an expert in this field that has nothing to do with cosmology, but I'm going to apply my stuff over there and has no clue about the subtleties of cosmology, or astronomy, or astrophysics, or whatever.
demands that there is a hexagonal planar lattice.
I would like to see the data on this.
Okay,
I would like to see the data. I would like to see the publication.
We can.
It should be abundant. I mean, it should be like, we should be teaching that there's a flaw in Planck. Let's stop talking about cosmology, because we haven't really been talking about cosmology, let's be honest, right? We're talking about something to do with black bodies, which may have some, we haven't gotten to real cosmology.
Well, this is essential theory. This is a piece of evidence at the heart of cosmology.
I would like to see something, and if you say that peer review is bogus, and
no, that's not what we're saying. That's not what I'm saying.
So you will be able to provide me with peer-reviewed articles, not necessarily by Sheila.
No, Brian, we want to write that peer review article with you. You don't understand. Like, we're literally sitting here and we're like, Brian, you are brilliant. you are at the top of the world, you should look at this, because this is the future of these ideas. And you are the guy who's going to write this, and you are going to revolutionize science, because no one has paid attention to this. Like, there's some people that we know, and I'm like, Brian, somehow everyone has missed this, and it is crazy.
Do you know you sound crazy?
I know.
Yeah, okay.
Okay, this is why I wanted to do this video, because this is kind of crazy. Well, there's no evidence to point to that there's carbon lattices doing this in space, and they don't have any proof to it, and they think, oh, we're going to write this paper, we'll work together, and everybody's going to take us seriously because Brian Keating's name is associated, a cosmologist. If he wrote this paper and it came out and it didn't work, he'd probably be a laughingstock in his community. And that's one of the reasons why he probably doesn't want to do it, because he doesn't want to come out as being crazy.
I know,
Fine.
but I'm telling you, it sounds insane, but it is
Copernicus
true.
sounded crazy too, you know.
And I'm literally
I
coming
get those
here.
He didn't
emails
get a
too.
Nobel Prize either, by the way.
Yeah, exactly. But you know.
But I'm like,
but
but Brian,
Tesla was crazy, and Boltzmann was crazy, and he killed himself. Right. Okay.
And now it is
You
our
also-
turn
They
to
were
do
right.
statistical mechanics.
Yeah.
I'm like, look, I know that it sounds like a philosophical distinction, where I'm like, hey, the black body thing here is important, and the lattices are important, and the structures are important, and that's why we're here, because we're like, Brian, no one is looking at this. We have been reading Planck. We have been looking at fundamental physics. We have been studying the
I
nature
don't
of
think
light.
you should read Planck. I think you should read modern statistical mechanics, modern plasma physics studies. I think you should visit tokamaks. I think you should visit other.
They don't make
reactive-
black body radiation.
They pull their
I know you guys are
universe.
saying that, but you have to be 100%.
Okay. He's got a point here. A lot of cranks go back to the original authors and go, well, this is the original author said such and this one said such and such, and they ignore all the research that's happened since then and all the evidence that points towards that. Robitaille, who's their I don't know what to call it, in Flat Earth they call them what is it? No, Flurf Daddies or whatever. Papa Flurfs. I don't know what to call it. Papa Crank is Robitaille for these two, so.
And bulletproof confidence
Would you take-
that it's completely impossible to.
I wouldn't
for
have
the-
come
for
here
the-
if it was possible.
Well,
I wouldn't
I mean,
have.
I
I wouldn't
don't
have said such.
Well,
such
guys,
Can we ask
you're
AI?
confusing
Can we
something.
ask AI?
No, because AI will tell you whatever you like. AI told me, ChatGPT told me that I wrote A Brief History of Time. It literally said,
Amazing.
that was one of the books. I said, thank you, ChatGPT. Can I have 1% of his book sales, please? No, that's one of the big red flags, by the way, to your audience, because I do offer. So what I've done is when people want to have their idea and have me share either in a Nobel Prize or something, or in the discovery of all time, really. It sounds like what you're claiming potentially could be a discovery of all time, right?
I
get 10.
I don't think so.
Well, it's a monumental. I mean, you're talking about Copernicus. You're talking about a lot of big name people, and I'm saying, if this is true and is revolutionary, yes. So you would want me to be a part of it. I'm honored to think about that. I get 10 of those a day, right? So one of the first things I do is someone sends me an email. I literally did this before this interview. I have an autoresponder on my phone. Someone writes me this. They have this paper they want me to read. I say, thank you very much for your email. I'm very overwhelmed with my own research, education, family topics, travel, and all writing and doing all sorts of other. Plus, I have a podcast, by the way. I don't know if you knew that. But I'm willing to evaluate your theory or your idea. I charge $1,000 per hour, donated to a food bank on campus at UCSD. I don't get any of the money. It's donated to the Triton Food Pantry. I'm a huge supporter of it because tragically, some of the students here are food insecure. First hour is $1,000. Next hour is $2,000, $4,000. Keeps going up like that. Take as much time as you want, as long as it works with my schedule. And uniformly, I've gotten many people to do this. Many people have submitted, put their money where their mouth is. Not just come here you guys put a lot of effort into coming here. I'm really appreciative of it. But put thousands and thousands of dollars towards the Triton Food Bank. So the students here should be grateful to these generative ideas, right? Not a one of them did not have their reviews, their thoughts or ideas reviewed by AI. Okay, multiple AIs. And what's interesting is all of them were substantiated by the AI, and more than that, the ones that are in conflict with each other, because I get them all together at certain points.
We see this
They're
too.
they're also consistent with ChatGPT or with any AI or Gemini and multiple AIs, right?
It is crazy.
It tells us nothing about it. So
Well, it does
that
have-
is not. We could say a fact. Like you could ask.
I would just ask it.
Plasma?
Just treat it like Google. That's
Yeah,
all.
like-
Yeah.
Well, but it also hallucinates. So Google, theoretically won't hallucinate. If we look up, but that's why I want to restrict the domain of what we're talking about to peer-reviewed. And you're going to say, well, it has nobody to peer review it. Well, that could be a sign that you're not barking up the right tree. You have to admit that, right? I could be wrong. You guys could be
Well,
wrong.
it's a first principle argument more than an appeal to any particular body of literature other than the classics that we're all aware of. I think actually, like for us, the best case scenario is just that you see what we're saying, not really that you. I mean, you can say it's stupid or useless or has
I mean,
nothing
outside
to
just
do with.
offering to have me involved in it and stuff like that. But I'm not an expert in black body. So again, I judge my students. I judge my PhD. I judge the people that submit their theories to me by the quality of at least the legwork that they've put into it. Now, you talked about your research into lattices and whatnot. Great. So you've done something, you've done domain. But if you did your homework, you would know I'm not an expert in lattices and carbon and stuff like that, nor would I claim to be. I am an expert in experimental cosmology, radiometric physics, atmospheric phenomena, absorption.
No, dude, you're a
all sorts of
complete badass.
No,
Like that's why we're here. Is we're like, yo, dude, there's something really crazy we noticed, and like I think it's important.
But why not go to an expert? Go to a plasma physicist. Why not go first to a plasma physicist, someone to talk about all these different things, and then go to other people? Like, I mean, you just said something that's.
What do you think our podcast is? Like, that's what we do. We do it
but I mean, you
twice a
talk
week.
to people that are not necessarily domain. If you talk to Terrence Howard about the CMB, that would be a big mistake, right?
No, we talked to Terrence Howard about his theory.
You talked to him about his theory, right? So I'm not a black body historian, right? So I'm confused why you're talking only about that. Like if I was on
terrible
talk,
because I feel like I'm upsetting you, and I just thought that we'd
It's
tell
not
you something.
upsetting, no,
I thought we
it's-
might just point something cool that maybe you would roll around in your head, and maybe you would make
I would have liked to talk about that for 20 minutes. Yeah, I feel like we spent the whole time, which is coming to an end, not discussing my research, not discussing new findings, not discussing the exciting developments in this field, but slightly coming to it from a perspective that, we may have all gotten it wrong because of this one weird trick that, Planck
Well, we
noticed.
have a chance to get it right, man.
But again, so I would say that's great. But like, if you guys have some idea that cancer is caused, in the bloodstream by your carbon, nanotubes in the environment, microplastics or whatever, and you're talking to me, I'd be like, these guys don't know what they're talking about, because they're not talking to an expert in that field or someone that can give them any credence to it, other than defend my priors, which is that the universe has abundant evidence, which I haven't even had a chance to get into. That does frustrate me. For abundant sources of evidence that the universe has this, and every time we pivot to it, you guys are kind of like, well, this is only true, for things, and we really the Planck satellite and WMAP should have built this other thing that would have made it possible. I mean, once you measure the parameter, there's absolutely not. We don't go out and measure 21 centimeter radiation from all these different locations because it could have been caused by some other effect, and build every instrument has to be a 21 centimeter radiometer, right? That's impractical. And once you measure something in science, the burden is on someone who's challenging it to provide substantiation that it's not constant, right?
We actually might have a millionaire who's going to help us build a satellite to go measure them. And it'd be really interesting because I don't think it will tell us whether it's a cosmic source or a local source.
I think the millionaire is Jim Allen. He designs computer chips designed computer chips for AMD and Apple and Tesla.
Which would be really cool because it will contribute to us not having to ask such a stupid question as to whether the CMB is there at L2. Right? So that'd be really cool.
So if we had more time, I would say, because I told you I have to leave it.
We'll come back next year.
Yeah, you're more than welcome to come back. and next year, you should have, by all rights, a lot more evidence, and maybe we'll have just like some. I mean, you cannot tell a credentialed scientist that his or her credentials don't mean as much as someone who has an interesting idea, who's read a lot of papers, who's incredibly invested in this topic for reasons that may be of interest to them, may be of interest to the whole world, in correcting some big mistake, right? You can't go to an oncologist. Again, go to an oncologist and tell them everything they know is wrong, and we have an idea that they're wrong. We can prove it. We do need their help to do it, and then the work that you're trying to do is in plasma physics. I mean, it's going to be something that's going to not sit right with the expert, right? Expert is somebody who's very, hold on a second. An expert is someone who's excluded so much potential knowledge that he is or she has made a complete career out of one very narrow aspect of their lives, right? So because I'm a cosmologist, it doesn't mean I'm a black body expert or anything. But within the domain of cosmology, we can talk about black bodies. We can talk about what's been measured, right?
I hear you.
Yeah.
And
so
I mean,
I think this is all,
I think, hold on. I think that you're letting him off too easy. I know, I'm sorry.
He's never gonna let us continue this conversation.
Well, I do have to go
Ryan,
babysit
you
some kids. Right?
Study the CMB.
Yeah.
Like, it's not an irrelevant question to you to be like, hey, hold on. Can we talk about the first principles of physics that go into the signal?
I would, but I'm just not convinced that, to be honest, as friends, I do enjoy talking to you guys. I think you guys do something very valuable. You've made a couple of factual errors.
Okay, let me write. Can I write those down?
The fact that lattices are the only possibility of a black body is in a specific carbon lattice.
I didn't say. I didn't say that. I said a planar hydrogen lattice.
A planar hydrogen lattice now?
No, sorry. Hexagonal. I had the H.
Okay, so hexagonal. Okay, so fine. But then when I ask you, like, can you show me some peer-reviewed refereed data, publications, eminent scientists?
Is probably the best source, right? Because they're going to tell you what the best black bodies, and you can see that they come from these, first of all from lattice-bound.
And you've also said that
condensed
gases
matter.
cannot be black bodies. There's no black body whatsoever, but you've also said it could be a gray body, so it's not really clear.
Gases wouldn't give you gray bodies either.
There's no and plasmas can't produce. You said that the plasmas aren't produced in tokamaks. You've said there's no characteristic
plasmas
temperature.
are produced in tokamak.
Right, but the plasma doesn't has any temperature.
Yeah.
So the temperatures that they speak about when they create a plasma, what are those temperatures of?
The intensity has some non-Planckian frequency distribution.
The temperature is only discussed in the context of molecular or ionic physics, in the average kinetic energy of a typical particle, of a typical molecule or ion.
So you won't get that nice fingerprint line spectra that you do from the black body from these.
Well, there's no fingerprint. I mean, black body is defined by a complete absence of spectral features.
Well, no, it's this nice, beautiful line shape, right? It has like.
You mean the Planck shape of the curve?
Yeah. Intensity versus
but there's no
temperature.
fingerprint. I mean,
that's what the fingerprint is.
That's
the Planck
chemical
shape.
fingerprints we typically talk about as emission absorption spectrum of atoms.
Right? But this is the emission absorption spectrum.
And that's how we measure, by the way.
Atoms,
right. So when we measure the sun and we measure its temperature, we are measuring what? What is it producing? Where does that temperature come from?
That's also a very well.
It's not a. You agree? It's not a hexagonal lattice, right? The sun is not a hexagonal lattice.
Let's talk about that next time.
Okay. All right. Well, this has been fun. I'm gonna go out and suntan later on in a non-black body. But thank you guys for coming out. Show your friends the Keating medal, because that is what I want to present to you here. I will show it to you guys.
All right.
So the Keating Medal for Impossible Imagination, featuring Sir Arthur C. Clarke on the front, and featuring Demystify Science with today's date, December 18th. You see this? This is not just some generic thing here, guys.
Got a bucket of
and this is a monolith from 2001: A Space Odyssey. So thank you guys so much for coming. Enjoy your Keating Medal for Impossible Imagination.
Thanks for putting up with us, man. I appreciate it.
It's fun. Happy New Year, healthy New Year, and let's do it again exactly at this time.
We'll be here.
Okay, I'm just gonna say a few things. He actually handled these guys excellently. I'm not an expert in cosmology, so there's a few things above my head, but I just don't get why people have to try to have issues with this stuff. There's a lot of evidence for it, and it works. And here's the thing, I've got to get my watch hours up. I know people don't really like watching this stuff. It's a little dry and not interesting, especially when I'm not making jokes. I'm not like there's some people like MC Toon and Craig who like making fun of people while they're debunking. But this is going to be fairly dry, and there's other people to talk about, and it should be done in a fairly civil manner. You don't have to start a fist fight unless you're Mikey Smith, but I know he's never had a fist fight, but he's tempting people to try to hit him. So okay, I hope everybody has a good day and good night, and see you later. And I'll probably maybe chopping this up for shorter videos, but I hope everybody has a good day, and goodbye, and see you next time. And who knows, it could be as soon as tomorrow night, but we'll see.